Okay, good evening everyone. I am Bin Kwan, Chair of Quantum and Introductory Seminar Manager of QISCA. It is my pleasure to introduce today's introductory seminar speaker, Daniel from SQRT. Daniel is a senior in the Department of Physics and Astronomy at Seoul National University and a lab member of the Oshalam Group led by Professor David Oshalam in the School of Molecular Engineering at the University of Chicago. Daniel's research centers on NV centers and condensed matter physics and quantum benchmarking. Today, he will be presenting a talk titled A Dummy's Guide into Quantum Sensing, sharing insights from quantum sensing by Dengen C. L., F. Reinhardt, and P. Capellaro. Then let's welcome Daniel to the stage.
Thank you for the kind introduction. As I introduced, I'm Daniel O, and I'm the Vice President SQRT. And today I would like to talk to you about sort of a niche topic that hasn't been covered, which is called quantum sensing. Now, most of you may have heard about quantum computing and quantum information, but a lot of you probably haven't heard of the topic of quantum sensing. Well, quantum sensing can be summed up in one sentence, which is basically quantum computing reversed. So in the case of quantum computing, you want to use the qubits to do computations. So you don't want the environment to interact with it. But in the case of quantum sensing, we actually deliberately use the environment to interact with the qubit, and then we see how the qubit changes in order to sense some quantities that come from the environment. So today I'm going to talk about the basics of quantum sensing, the definition of quantum sensing, and some basic quantum sensing protocols, and an example of quantum sensing using an actual quantum platform. Okay. So what is quantum sensing? Sorry about that. What is quantum sensing? Well, quantum sensing can be defined as the use of a quantum object or quantum system to measure a physical quantity. So basically, what you do is you take your basic quantum system, and then you have something that's called a signal, which we're going to call V. And this signal is going to interact with this system. And as it interacts with this system, what happens is that the energy levels of the system changes. And by observing how the energy levels change according to a signal, we can therefore infer we can reconstruct what the original signal was. Well, can we do this with any quantum system? Well, there are a few conditions. First is that they obviously need to be discrete energy levels, of course. And the second is that initialization and readout should be possible. I'm going to cover more in detail what those means, but basically we should be able to initialize the system into a state that can interact with the system. And then we should be able to change the system into another state that can be used to measure what the final state of the system is. And the third condition is that it should be able to be manipulated by time-dependent fields, i.e. our signal. So it has to be able to interact with such a signal. And the final condition means that the energy levels has to change. So sometimes you could have a signal, but it won't interact with the system at all. And of course, you can't use that system to sense any external quantities. So how do you actually do quantum sensing? So now you have your signal and you have your system. And what you do is you let the system and signal interact. And what happens is that you get this final Hamiltonian, which is comprised of three parts. Now, the first part is obviously the internal Hamiltonian, the Hamiltonian of the original system before any interactions occurred. And the second Hamiltonian is what's called the signal Hamiltonian, which basically refers to our signal, basically the system of our signal. And the third is the control Hamiltonian, which represents the quantum gates we use for initialization and readout. So as we change the system, we actually need to change the system in order to first make it able to sense, which is called initialization. And then we change the system slightly again so that we can actually measure the result, which is called readout. So the first term is the original system. The second term can be thought of as the interaction Hamiltonian, basically the Hamiltonian that represents the interaction, the system, and the signal. So the first two terms actually is what's important. So normally, the H0, the original Hamiltonian, the internal Hamiltonian, has this form for a two-level system in the simplest case. And the interaction Hamiltonian can normally be represented as what's called a Pauli Hamiltonian. So if any of you have taken basic quantum mechanics, you'll know what the Pauli matrices are. And some of you may know that the Pauli matrices form a basis of the 2x2 matrix space. So this is basically saying that this Hamiltonian is an arbitrary 2x2 matrix. And the Pauli basis for this matrix space is quite convenient. So that's the reason we're representing it this way. So this means the dot product between our signal, which is usually a vector, and with the Pauli vector, which is comprised of the X, Y, Z Pauli matrices. And you'll see this gamma term over here, which I defined on the first slide, and that's called the coupling parameter. This represents how well the system changes according to a given signal. So most of the time, you would either be measuring Q equals 1, which is the first derivative, or Q equals 2, which is the second derivative. So you normally measure Q equals 2 in cases where Q equals 1. In the case of Q equals 1, the coupling parameter is 0. So obviously, you can't extract any information from that. So in that case, you use higher orders of Q, such as Q equals 2, or even very rare cases, Q equals 3. So that's what the coupling parameter is, basically the measure of change of the system according to the signal. And the goal, obviously, is to reconstruct the original signal from the changed system. So our basic general procedure will look something like this. We initialize a system into a known basis state. So for example, let's just call this state the 0 basis state. And then we will transform this into what's called the sensing state. So this is a state that can interact with the signal. So sometimes the original system, this basis state, can interact with the signal. So we're used to transform it into the sensing state. So this is what's called initialization. We're transforming 0 to psi of 0. And then the third step is called evolution. So we're evolving over this, the total Hamiltonian here, which is basically interacting the system with the signal. And then we, of course, after evolving, after a certain amount of time, we need to know the result. So in order to do that, we transform the state into what's called a readout state. A readout state, which is a state that our measurement equipment can actually read out. And then we measure what's called the probabilities of these states. So we actually use this value of P. So we measure it many times and we extract this P statistic. And then we use these different ensembles of P to reconstruct total signal V. So that's the general quantum sensing protocol. So the basic, so here are a few examples. The most basic quantum sensing protocols was called a Ramsey measurement. So this is the bread and butter of quantum sensing. And it's used in cases when you want to measure a DC signal. So for example, if you just had a static magnetic field, for example, maybe the Earth's magnetic field could be an example. So in this case, what you would do is that you have your two-level system and you have the transition energy, of course, and there's a frequency between those two energy levels. Let's call that omega 0. And then we, of course, it's initialized into the ground state. But for the Ramsey measurement, the sensing state is actually the plus state the X basis state, so over here. And of course, you would do that by applying a Hadamard gate. So of course, depending on your system, how you would apply this Hadamard gate would depend on from system to system. But most of the time, you would apply microwave pulses of a certain length. So in many different quantum sensing protocols, platforms, for example, superconducting qubits or spin qubits, you would use microwave pulses of a certain length to apply what's called a pi over 2 pulse, which I'm going to get into detail a little later, to perform what's called a Hadamard gate. And then you would let this state evolve for a certain amount of time. And then you would get this final state over here. So basically you get this relative phase over here. And then you transform this into the readout state, which is the Z basis. Basically, you need to transform back into here. And then you would, when you read out, you get this probability of measuring 0 over here. And then from this probability, you can reconstruct omega 0. So basically, this is what the Ramsey measurement does. It measures the relative phase according to a DC signal. So in this case, without a signal, like 0 signal, you only get omega 0. But if, for example, you had a magnetic field, you would get an additional relative phase added onto here. And by measuring this, you would get omega 0 plus that relative phase. And then subtracting omega 0, you could figure out what your original DC signal was. So this is your basic Ramsey measurement. And is often used in practice to measure static magnetic fields. So another measurement, another fundamental measurement, is what's called a Rabi measurement. And some of you who've taken advanced quantum mechanics may have heard of what's called Rabi oscillations. So it's basically just doing that. It's measuring Rabi oscillations. So in this case, it's used to measure the transition element of a signal. So how it transitions from 0 to 1. And in practice, it's very useful for calibrating pulse lengths, as I mentioned earlier. So I mentioned earlier, to perform rotations, to perform gates such as the Hadamard gate, you need to know the length of your microwave pulse. So you find out the length of your microwave pulse through Rabi measurements. And for simplicity, let's just assume that internal Hamiltonian 0 is just constant. So in practice, it would just be like a one-level system over here. So we would initialize into 0, of course, and then the sensing state is just still the 0 state in this case. And then we let it evolve according to this Hamiltonian over here, which is basically the transition between 0 and 1. So this Hamiltonian basically tells you to take the 0 state, transition into the 1 state, and take the 1 state and transition into the 0 state, because it's a Pauli X matrix. So if we evolve the entire state according to this, we get this final state. And then transforming this into the readout state, which is just this state over here, we get this probability right here. And through this probability, we, of course, can extract omega 1. And in practice, this is basically a Rabi oscillation right here. So if you view the signal, you would find this oscillation between the 0 and 1 state. So the probability of measuring the 0 state would oscillate over time. And then you measure the time. For example, if I wanted a pi pulse, which transitions from the 0 to 1 state, I just measure how long it takes for the probability of measuring 1 to be 100%. And that would be the length of your pi pulse. And so the length of your pi over 2 pulse would be half that length. So that's how you calibrate pulse lengths using Rabi measurements. And so this is basically equivalent to performing an X rotation at an angle of omega 1t. So as you wait a certain amount of time t during your measurement, you're altering the rotation angle. So intuitively, basically what you're doing here is, say you're starting in the ground state, and if you apply a pi over 2 pulse, it rotate this around the x-axis over here, right, which is here on the block sphere. So it moves from here, the 0 state, to the plus state. And if you apply the pi pulse, it would move from the 0 state to the 1 state. So in order to figure out how long you have to apply your microwave pulse in order to get these rotations, we use gravity measurements, basically. So basically what happens, you do gravity measurement first, and then we use the calibrated pi pulse length and to apply the half pi pulse lengths when doing your Ramsey measurements. Okay, so we've seen how to measure DC signals, such as static magnetic fields. But a lot of signals in practice are not DC, they're AC. So the problem with using Ramsey measurements when trying to measure AC signals is that AC signals oscillate. So the measurement results of the Ramsey measurements, they cancel out to zero. So basically you get nothing when you try to measure a Ramsey measurement for highly oscillating fields. So in this case, you need a different protocol. And then these protocols are they're called dynamical decoupling sequences. So let's say you have this basic AC signal, which is a cosine function with a phase shift. And then you can represent the final state after evolution like so. And then after evolving, you notice, of course, there's a relative phase here. And this relative phase can be represented as this integral right here. So you'll notice this integral actually goes to zero if you wait an entire period, which is why you can actually measure AC signals using Ramsey measurements. So the strategy here is the first basic strategy you can use is to use what's called a hand echo pulse sequence, which is basically adding a pi pulse in the middle so that the minus components don't cancel out, but instead add together. So you get a non-zero component over here. So it's basically just changing the sign of this integral over here. So we're basically splitting the entire measurement time in half, and then we're changing the sign to negative, and we get this non-negative value. So that's a hand echo here. So intuitively, you can imagine that of course, we start with the ground state, hit with a pi over 2 pulse, and then it starts rotating because it's evolving. And then in the middle of the evolution, you hit it with a pi pulse. So it's rotated 180 degrees, and then starts rotating the other way. So basically, it starts rotating this way, but if you hit it with a pi pulse, it rotates the other way, so it cancels out the evolution that was previously there. And so you end up with a non-zero component over here, and through this component, you can reconstruct the original signal. So we can improve upon this, obviously, by adding lots of different pi pulses instead of one. So let's say instead of cutting it into two, you cut it instead into n different intervals. And then in those intervals, you add a pi pulse right there. So basically it's evolve, you hit it with a pi pulse, evolve, hit it with a pi pulse, and you do this n times. So that's what's called a CP sequence or a CPMG sequence, which is named after Carr and Purcell, who discovered this. So it's basically a hand echo with lots of different pulses inside here. So the pro of doing this is that you can increase the sensitivity of your measurement, basically. So in the hand echo, you have to wait over to t over 2 over here, and then you hit it with a pi pulse. But the problem is that during this evolution, some noise can get in, basically. So external signals can alter the phase, and then when you hit it here, you expect it to completely cancel it out, but instead, due to external signals, there's still some noise and error left in. So in order to combat this, we simply increase the number of pi pulses in order to reduce the number of time that external influences enter our original signal. So of course, there are two different versions, of course. So there's the original CPMG sequence, in which, let's say, the delay between these pi pulses is tau. The delay between the original pi over 2 pulse and the pi pulse is half of that. So that's a CPMG sequence. If they're all evenly spaced, they're called what's called a periodic dynamical decoupling sequence, PDD over here. And then in practice, these two are basically the same. But for some signals, a PDD sequence, for some physical systems, a PDD sequence gives you less noise. And in some other systems, a CPMG sequence gives you a better signal. So Yeah, and you can reconstruct the original signal instead of this V over here, as you notice with the Hahn echo, we get this W term over here, which is called the weighting function. Basically, it represents how much the phase changes after a certain amount of time for a different pulse sequence. So basically, there are lots of different pulse sequences apart from these two, and each pulse sequence has a weighting function. So you can actually engineer different pulse sequences to fit your own needs for quantum sensing. And these pulse sequences have their own weighting function, which determines how much dephasing there is after the evolution. So we've covered how to sense AC signals. I think this is the final topic. Yeah, the final topic is noise spectroscopy, which is basically measuring noise, measuring noise and determining its characteristics in order to combat its effects, or measuring noise in order to sense even weaker signals that are hidden inside of that noise. So noise spectroscopy, well, when dealing with noise spectroscopy, we define noise as a Gaussian stochastic signal. So if you have a signal that isn't Gaussian, basically that isn't a random walk. So if the noise is correlated with each other strongly, the methods I'm going to show you right here, they don't work at all. So just keep that in mind. So we're going to define noise as a Gaussian stochastic signal. And then sensing these signals is basically noise spectroscopy. So we're sensing basically noise over here. So there are a few mathematical definitions you need to know, but in practice, you don't actually need the actual formulas, is that what's called the autocorrelation function and the power spectral density. So intuitively, the power spectral density is defined as so with the autocorrelation function. This basically measures how much a signal is correlated with itself. And this basically represents the decomposition of the noise signal. So basically it measures how different signals of different frequencies add together to comprise the entire noise signal. So basically this is the fingerprint of the noise. So different types of noise has different signals. And then using this, you can define what's called a filter function, which is represented in this y expression. And this is used to define what's called the decay function. So basically, the decay function is what you need to pay attention to, because this represents how the transition probability decays. So this is what we're actually measuring. We're measuring how much the probability to measure a certain state, such as the 0 state or the 1 state, decays over time. And then we use this decay to decompose the decay function. And from this decay function, you can tell what type of noise caused the decay. So this may seem a little bit abstract, but to give you an example, as I mentioned, the decay function is characterized by the type of noise, and we measure the decay function by the transition probability. And normally, you get this sort of form for the decay function. So some transition frequency times t to the power of a plus 1. So the value of a basically determines what kind of noise it is. So if you have a value of a equals 0, it's what's called Markovian noise, which is basically your average random walk noise, basically. So basically, for example, the probability of me giving a random transition would be like flipping a coin, basically. P equals 1/2. And it doesn't matter what the previous results are, the noise signal is still going to be the same. So there's no correlation between any of the noise. And second, if you have A equals 2, it's what's called Lorentzian noise. And it's called Lorentzian because the filter function, it was called Lorentzian because this power spectral density has a Lorentzian peak in its spectrum. And if A is 1, it's what's called 1 over F noise. And that's because the power spectral density scales as 1 over F as its frequency. So if in the log scale, we would have a slope of 1, basically. So basically, in short, through measuring the decay function, the probability, you can tell what type of noise is in your system. And by doing that, you can characterize what type of external influences you can get rid of. So basically, through measuring this decay function, through this lengthy mathematics, you can reconstruct a filter function. So for example, if I applied a CPMG or PDD sequence, this is the filter function for these two sequences. So every sequence also has a separate filter function, which basically reconstructs what your decay function will look like over here. The relationship between this power spectral density and this decay function. So I measure this, and then measuring this, I can reconstruct this, basically. So from measuring the decay of the probability, I can measure S of V, and S of V tells you what type of noise you have. So basically, the basic protocol would be I would apply the CPMG sequence as noise is coming into the system, and then I would observe the decay, and from this decay, I can reconstruct SV. And SV, as I said earlier, is the fingerprint of your noise. And through this fingerprint, you can tell what sort of noise is entering your system. So for example, of course, the basic procedure is called relaxometry. So basically, you apply a sequence and you wait for noise to come in, and then you see how the system changes. So it's basically another word for quantum sensing, except the signal is not the signal we want to measure, but it's a noise instead. So T1 relaxometry is basically you give it initialization and you read out the final state. That's it. So it's basically a transition from the excited state to the ground state. And then you can measure the time it takes to transition from the excited state to the ground state. And then you can then reconstruct the noise spectrum over here, T1, from the T1 time. T2 relaxometry basically probes how much the phase dephases according to noise. So as I mentioned earlier, you initialize it in this state, then you rotate it, and then you get what's called dephasing noise, which basically changes the phase. That's why it's called dephasing. And then you wait for a certain amount of time until the original phase is completely depleted, and then you rotate it back and you read it out again. And then the time it takes for the original phase to be completely erased is called what's called the T2 time. And then the T2 time is related to the signal as so. So basically, from measuring this single quantity, you can measure this power spectral density, which is related to your decay time. So if I know T1, I know this, and since I know what sequence I have, I then know this decay function. So I can predict in the future how much this noise will affect my system in the future, even though I haven't measured it for that amount of time. So the final topic is going to be sensitivity. This is related to measuring the sensitivity. So as I mentioned, you can measure the T2 time and T1 time. And then the T2 time is defined as just using a Ramsey sequence. But of course, as I mentioned earlier, you can add different pi pulses in here to increase, basically to reduce the effects of dephasing. And that's called the T2 star time. So by using the T2 time or the T2 star time, you can calculate what's called the sensitivity. So a lot of quantum sensing literature, they're going to mention the sensitivity, basically how sensitive your sensor is to external signals. And you can estimate the sensitivity by measuring the T2 time or the T2 star time, basically. So by measuring this quantity, you can estimate what's called the signal to noise ratio, which is the ratio between the signal and the amount of noise you have in your system. And you want this SNR, the signal to noise ratio, to be as high as possible, obviously. But a good benchmark for most quantum sensing protocols is around 10. So that's basically the golden number you're aiming for in your SNR. But theoretically, if it's over 1, you could do it. But in practice, it needs to be a less 10 to get a meaningful result. So if your SNR is less than 1, obviously, there's more noise in your system, so you can't extract a meaningful signal from that. And then I'm not going to derive this, but the original SNR definition is basically the change in your observed transition probability divided the variance. But if you calculate this, do some mathematics, you get this term over here. So this SNR is related to the decay function, which is related to the noise. And you can reconstruct the decay function by measuring the T2 star or the T1 time, as I mentioned earlier. So from this SNR, we can define what's called the sensitivity, which is the minimum detectable signal with an SNR of 1 per unit time. So as I mentioned, the theoretical limit is 1. So the shortest signal I can, if I reduce the signal, obviously the SNR is going to fall. And the smallest signal I can sense would obviously be the SNR that has a value of 1. So this is the definition of sensitivity is basically the smallest signal I can measure that has an SNR of over 1. And this defines the limit of our quantum sensor. So basically, you just need to memorize that the sensitivity is inversely proportional to the square root of the T2 star. So as this T2 star decreases, I'm more sensitive. As T2 star increases, is less sensitive. So to wrap up, there are different quantum sensing platforms, obviously, as I mentioned. So these are the major ones. So you can use what's called solid spin qubits, which basically consists of a defect with a spin system, which you can manipulate. And then you have superconducting qubits, which can be used for quantum computing. What time is it? Yeah. What can be used for quantum computing, but they can also be used for quantum sensing because they are a discrete energy level system, which of course is affected by external signals. You can also use neutral atoms and trapped ions. So basically any quantum computer is itself also a quantum sensor. But quantum sensing is easier to do because you want to let the system interact with the environment. So that's why quantum sensing is considered the first candidate out of all the quantum technologies to have actual practical real-life applications. So when I was in the Osham lab, the US Department of Defense asked for ideas for quantum sensing using this NV Center platforms to be installed in the military helicopters or military aircraft. And of course, there's other quantum sensing work, of course, regarding in the field of biosensing. So most of the time when you want to sense really weak magnetic fields that come from the brain, you need a lot of bulky equipment because previous sensors, they require a very low temperature. In order to reach that temperature, they needed a lot of bulky equipment. But using NV centers, these can be miniaturized quite easily. So by miniaturizing these, putting them in someone's brain, you can theoretically perform the same sensing of those weak magnetic fields using a lot less external equipment. So yes, in the interest of time, I'm only going to skim over these as this is an example quantum sensing using the NV Center platform. So basically, the NV Center platform consists of different levels according to their spin states. So if they have a spin state of S equals 1, it's called a triplet state. If S equals 0, it's called a singlet state. And a triplet state has 3 different states, 0 state, and a plus, a minus state. And these can be used for quantum sensing, obviously. And then we use what's called optically detected magnetic resonance in order to do that. So the basic gist is that if I start in the 0 spin state and I excite it using a laser, it just comes back down and releases radiation. But if that state is instead in the 1 state, which I excite to using a magnetic microwave, I can then, and I excite it again, it does what's called an intersystem crossing. By going to a singlet state first, and then going back to the ground state. And when it goes to the singlet state, it doesn't release radiation. So basically, you have a dip in the amount of light that is emitted, and that is what is exploited to perform quantum sensing. So what happens is that I apply a magnetic field. And what that does is that it increases the energy gap between these 2 energy levels. And then as the energy gap increases, the frequency at which this dip occurs shifts, basically. So this is what happens. As I increase the magnetic field, normally I only have one peak. I apply a magnetic field and it splits the energy levels, and I get two peaks. And as I increase the magnetic field, these peaks go farther apart. And as you can see, as the magnetic field increases, the distance between these two peaks increases. So using this ODMR phenomena, I can detect magnetic fields basically. And then through this formula, I can reconstruct the final strength of the magnetic field. So basically what you do is you apply a laser, and then you apply a pi pulse or pi over 2 pulse. It depends on what type of ODMR you want to do. And then you let it wait, and then you either apply another pi over 2 pulse or do nothing. And then you apply final laser to measure the final spin state. And then you get this spectrum over here. So using this protocol, this very simple protocol, as I mentioned, the equipment is so elementary and rudimentary, it's quite easy to set up. And that's why it's easy to miniaturize. And that's why there's so much interest in using the Envy Center platform as of recently. And it operates actually not at 10K, not at 300K. It operates at over 600K. So even if the temperature reaches 300 degrees Celsius, I can still perform quantum sensing. So I think that's going to be a wrap. And here's some references if you're interested. And I'll be opening the floor to some questions. Yes. Sorry. Definition of a filter function. I think I skimmed over it because I know some people were dozing off. So this is the decay function, and this is the power spectral density. So the decay function is measured from this, and the filter function is basically this function over here when you perform a Fourier transform into the frequency space. Yeah, it's the weighting function of this power spectral density, basically. Is how much you need to weight of the Fourier transform in order to reconstruct the entire decay, basically. Yeah, so as you change the sequence, this changes. So the noise isn't changed by the sequence, but the sequence changes this. So basically by changing the sequence, you can alter the sensitivity to this, basically to different frequencies. So by changing this, I can for example, if I wanted to measure a certain noise at a certain frequency, I could choose a pulse sequence that gives a larger weight to the value of SV at that frequency. So that's why this is called the filter function. It's filtering out the frequencies of noise I want to measure. That's what it's doing. Yeah, well, theoretically, you can do that, but sometimes the final sequence you need to do might not be practical using the equipment you have sometimes. So most of the time, we choose between different pulse sequences that have been shown to work in the literature for my quantum system. So, but in practice, most of the time, we either use CPMG or PDD sequences, but you can design your own sequences. And that's what's called basically pulse sequence engineering. So you can do that, but sometimes you need to be wary of what your equipment can do. Yes. Uh, yes. Yes. Hmm. So the amount of measurements you need to perform is usually dictated by the SNR you're targeting. So as I mentioned, most of the time you want an SNR of 10. So the amount of measurements increases the SNR as proportional to the square root of n. of course. So if I perform 100 measurements, like the SNR, let's say the SNR is like 10, and if I apply 10,000 measurements, it would be 100 times that, obviously. So what you do is you set your goal for the SNR, basically, and then you do some measurements, and then you pause the measurement. Actually, you can most equipment you can actually pause the microwave sequence, and you calculate your SNR, and then you determine your current SNR and then your objective, and then you use the difference in the SNR to determine how many more measurements you need to do. But most of the time, it's either like 10,000 to 100,000 measurements in practice. Yes, because this term on the square root is actually a square root of n, and n equals the measurement time divided by the measurement, the time per experiment, exactly. So that's the amount of measurements you're performing. Depends on the system, but for NV centers, it takes 2 to 3 hours. Yeah. Are there any further questions? I think there's a question from EQS. Do we measure for individual NV center qubits in multiple? Okay, so this is an interesting question. It's asking what's the difference between a single NV center and multiple NV centers? Well, most of the time for very simple measurements, you want to use multiple NV centers because it increases the amount of light that is emitted. So it's increasing your SNR. Sometimes you want, but sometimes if you use multiple NV centers, sometimes they strongly correlate with each other, which increases the amount of noise actually. So that's what I actually observed when I was at UChicago. We decreased the temperature, but when we tried to sense with lots of different NV centers, what happened is that they started interacting with each other, which increased the amount of actual magnetic noise. So you don't want too many NV centers, but using just one NV center at the, for example, the wrong conditions, you may receive a signal that's too weak that gives you a SNR that is not optimal. But sometimes they use single NV centers depending on what physics they actually want to like observe. For example, if I want to make a quantum computer using NV centers, the number of NV centers actually matters. So you have to couple lots of different individual NV centers. But if I wanted to measure like a really simple static magnetic field using multiple NV centers didn't have a huge difference than using a single NV center. If that answered your question. Okay, then yeah. Okay, if there, do you have a question? Okay. Yes. Yes. Well, for example, uh, let's say I measured like some noise you can eliminate, some noise you can't. Okay, so for example, Markovian noise, if I wanted to get rid of Markovian noise, you can do that very easily with a CPMG sequence. But, this is the but, if the noise is 1 over F noise, this is actually fundamental to quantum mechanics. So if I have a lot of 1 over F noise, that means I'm doing very good because other different types of noise isn't in my system. So I basically eliminated the total amount of noise I can. So if you wanted to try to eliminate this type of noise, it would be very difficult because it's against quantum mechanics. So you have Markovian noise. Lorentzian noise means there is some correlation, and this leads a bit more sophisticated pulse sequences. So to answer your question, sometimes you can, sometimes you can't. So this basically tells you what type of noise you have. And then some noise you can't eliminate, but some noise you can. So yeah. Yes. Yes. The fundamental limits of quantum sensors. Well, I do think the fundamental limit, well, there's a lot of components. Well, the SNR is a main component that you mentioned. Another component that is a hindrance is sometimes the size of the sensor itself. So sometimes I mentioned biosensing using NV centers. NV centers need to be inside, of course, diamonds because they're diamond defects. Sometimes the nanodiamonds are larger than the objects you want to sense, sometimes proteins. So there's actually new research going on at the Ausscheln lab at U Chicago, which tries to combat this because they try to biosense magnetic fields coming from different proteins. But nanodiamonds are so much larger than these proteins that you can't do it. So what they did was used another protein that's called a fluorescent protein. And this fluorescent protein happened to have an energy structure that's nearly identical to the NV center. So they could use the same techniques as the NV center to perform quantum sensing with that protein itself. And since the protein is a similar size to other proteins, you could get them to be very close and you can increase the concentration to increase the SNR. And then they were able to perform like, yes, femtotesla at liquid nitrogen temperatures and picotesla at room temperature sensing, basically. So another like hindrance to quantum sensing is sometimes the size, the geometry of the sensor itself and the SNR. Of course, there are fundamental limits, as you mentioned, in quantum mechanics, such as 1 over F noise. That, of course, sets a lower bound on the sensitivity you have. But sometimes using different platforms, sometimes some platforms are suited at this temperature or this setting, that it's not like it's sometimes difficult to compare the two. So yeah. So
Okay, due to time limits, I think we're
yes.
going to wrap up now.
Okay.
Okay, thank you again, Daniel, for the excellent talk. And we're going to take a 5-minute break and continue the next journal club session. And we are going to start at 7:55. Thank you for the excellent talk.